Welcome you again for this course, that is Fundamentals of Compressible Flow. We are in the module 3, which is a new module. This title of this module is quasi one dimensional isentropic flow. So, the content of this lecture are as follows, that is effect of area changes on flow properties, concepts of quasi one dimensional flow, governing equations for quasi one dimensional flow. Now, let us see that we have brought about a new word which is quasi one dimensional. So, in all previous sections we essentially emphasize the flow to be one dimensional in nature, in a sense that it is the flow is entering in a constant area duct. That duct in particular we assume to be a stream tube. In fact, the cross sectional area at the inlet and the exit are essentially same. Now, while analyzing the flow field, we really do not bother about how the flow is changing within the duct, rather we are essentially bothered about the inlet and exit condition of the duct. And while analyzing all those things, it is assumed that the flow is isentropic in nature. So, that is what we have analyzed till this point of time. Now, moving further, we are talking about the quasi one dimensional flow. So, in this approach I will explain that how it is different from the conventional one dimensional flow and why that word quasi comes into picture. So, before you move further, we will now talk about the effect of, we will bring into effect of area change on the flow properties. Rather, we will say that we have to do the relaxation of the one dimensional nature. So, to one simplest thing that we can do is that we can change the area, but still the flow can be treated to be isentropic. So, there is some thermodynamical physical insight into it. So, for which we will revisit the Mollier diagrams just to explain that how the area change, how we can do area change, while doing so the properties are going to increase or decrease, or there is a change in the flow properties. So, let us revisit this Mollier diagram. So, when you draw the Mollier diagram, we normally refer it is as a in enthalpy entropy plane as shown in this figure. So, on this enthalpy entropy plane, we are defining a state which is any arbitrary state 1, and we also will talk about a stagnation state 0. So, when I say the stagnation state, I can define a stagnation enthalpy H naught is equal to H plus u square by 2. So, for this case, if I for the state 1, any arbitrary state 1, if I can define this as enthalpy as H 1 in this diagram, and corresponding to the stagnation state I can define H naught as its state. Now, when I am at point 1, we are at pressure P 1, which is the any arbitrary pressure, and when we are at point 0, we are at corresponding stagnation pressure. So, this stagnation pressure P naught corresponds to the static pressure P 1. Now, looking at these equations, what we can say is that the total stagnation enthalpy is divided into two parts. One is the static enthalpy H 1, other is the dynamic enthalpy that comes by virtue of its velocity, that is u square by 2. So, in other words, what I can say, I can go from state 1 to 0. So, when I go from state 1 to 0, that means I am moving from I am moving isentropically. So, in this case for this process 1 to 0 or 0 to 1, essentially the entropy S 1 is equal to S naught. So, when we are moving from 1 to 0, that means we are increasing the pressure. Okay. So, relative weightage of u comes down. When I am moving from 0 to 1, the relative weightage of u increases. So, in one case I am accelerating the flow, in other case I am decelerating the flow. So, this is the very important basics, that one can accelerate the flow. When I say I have to accelerate the flow, then we have to go from state point 0 to 1, so that pressure must decrease. Pressure decreases, velocity increases. When you say decelerate the flow, this means pressure increases, velocity decreases. So, this is how we are this is the how the very basics fundamental things, that how the flow processes change when isentropically, when we are moving from stagnation state to a static state, or from static state to stagnation state in isentropic manner. So, this is how the Mollier diagram is framed up, in which the flow process with known initial properties and mass flow rate, the locus of all isentropic path can be traced in a Mollier diagram. So, that is a spelling mistake that can be traced on a Mollier diagram. And in this case, while accelerating or to accelerate or decelerate the flow, the driving potential for this variation in the flow properties comes through area change of the passage. In fact, while decreasing the pressure or increasing the pressure, we come across the change in the velocity, and to achieve this we must take into account the area change of the passage. Now, let us see that we will go one by one. The first thing what we are going to see is that on a Mollier diagram, we have to see that how an expansion process is taken place on a Mollier diagram. So, to study the meaning of flow expansion, it means that the flow path involves decrease in pressure with change in the area. So, the pressure must decrease in the direction of the flow with change in the area. So, that is what the flow expansion means. So, I like to emphasize this word, flow expansion means decrease in the pressure, and this through this process the area can increase or decrease. So, those things will come in the later part, but the basic understanding goes that when we say flow expansion, it must decrease the pressure. Now, to do this, so let us take a state which is going from 1 to 2. In the previous case, we say we are moving from stagnation to static or static to stagnation. Now, you are saying that it is any arbitrary process, we are moving from state 1 to 2, and this process is treated to be an expansion process. So, what I drew is that in the same Mollier diagram, that is HS plot, I am putting a point 1, that is coordinate 1, and point 2. So, we are moving in the direction of 1 to 2. So, in a manner such that you say S 1 is equal to S 2. So, the process is isentropic. So, when I am moving these things now on a Mollier diagram, these two lines represent the constant pressure lines. So, at point 1 the constant pressure lines can be represented in this manner, and for point 2 one can draw the constant pressure line in this manner. So, this is how it is shown in the figure. So, next important point is that and the flow process is isentropic. So, when I say flow process is isentropic, so for state 1 and state 2 we will have same stagnation enthalpy, that is H, which is H plus U square by 2 is equal to constant. So, this needs to be constant. So, what I can do is that I can draw another constant pressure line which can go in this manner, so that I can define this for this point 1 and 2, I can define a point O for which the total pressure line is defined in this manner and corresponding stagnation enthalpy is defined as H naught. So, what I can say, your H naught 1 will be equal to H naught 2, and this is nothing but S naught. So, entropy there is no change in the entropy. So, let us define the state point 1 and the relative weightage of H and U. So, for point 1 I can draw a line as H 1, which is this, and corresponding U 1 square by 2 we can write as shown in this figure. Now, for point 2 we say this is your H 2 and corresponding U 2 square by 2 is defined by this line. So, in this process what we can say, by maintaining total enthalpy constant, one can play with the relative decrease in the enthalpy or increase in the enthalpy. So, let us say if we are moving from point 1 to 2, what I am trying to say, I am in this process and the process goes in an isentropic manner. In this process I am decreasing the enthalpy. So, that means it drops from H 1 to H 2, but at the same time I am increasing its flow speed, that is from U 1 square by 2 to U 2 square by 2, or in terms of kinetic energy is increased. So, the increase in the velocity happens at the cost of decrease in the static enthalpy, and in this process I am going from 1 to 2. So, pressure must decrease. So, this means that I am expanding the flow, that involves decrease in the pressure, and in this process I am also increasing the flow velocity at the cost of static enthalpy. So, this is a very fundamental aspect, and we call this expansion process on a Mollier diagram, we call this as a nozzle action. So, when I say nozzle action, that means I must expand the flow, the pressure must decrease. Okay. Now, this is a mechanism in which one can increase or decrease the area whether your inflow is subsonic or supersonic, which means if my at the inlet state your velocity is subsonic, we can increase the velocity, or we can also for a nozzle action the velocity must increase and pressure must decrease. This is the fundamental aspects. Now, moving further, we will just take a reverse situation. So, there is nothing much to explain here, we are just saying that it is a compression process on a Mollier diagrams. So, we redraw the same figure. So, instead of going from so, I will just put the reverse symbol, like we are now at point 1 and moving to point 2, that is pressure must increase, but still your stagnation pressure remains same. So, direction of this is given as 1 to 2. So, there is a increase in the pressure. So, you have your H 1, you have H 2 and this is H 0. So, in this process we are saying this as H 1 plus U 1 square by 2 H 2 plus U 2 square by 2. So, here 2 dash and 2 and 2 dash are same. Okay. So, this process is known as, and in this case also your H 0 1 is equal to H 0 2. So, the function is just exactly opposite. So, this process we call as a compression process and it is called as a diffuser action. So, in this process what is going to happen, your static enthalpy increases, but flow velocity drops and the path involves the area change. So, it is a case of this is a change, the flow compression is a increase in the area. So, the flow compression involves a path that involves increase in the pressure with the change in the flow passage. So, there is a typo mistake that one can make it corrected. Okay. So, now we are able to say that process is isentropic and we can define the compression process and expansion process on a Mollier diagrams. So, accordingly we define diffuser action or nozzle actions. Till this point of time we do not say anything about the area, whether it should increase or decrease, that part, that aspect will come later. But for a nozzle action, the very bottom line, for a nozzle action pressure must decrease and for diffuser action pressure must increase. Now, let us do a kind of a relaxation saying that instead of talking the flow to be isentropic, we will say the flow needs we can say it is a adiabatic. So, when I say adiabatic, so I bring friction into account. So, in the same nozzle action we can think about a we can bring into friction. So, the essentially flow is not isentropic, rather flow still can be thought of to be a adiabatic. So, what does this mean? So, again we will revisit this enthalpy entropy diagram HS. Now, since it is a nozzle actions, so we define this point to be situated at the top. So, it is a expansion process. So, one is moving from 1 to 2 and had this process. So, I will define this state as 2 dash, okay. So, which is isentropic. Now, if the flow is not isentropic, the actual process, the flow can take place in a non isentropic manner. So, we say 2. So, the actual process we say it is a 1 2. So, obviously one can say that your S 2 is greater than S 2 dash. That means 1 2 process is non isentropic process. In this aspect we can say there is a enthalpy lost. So, this is nothing but H 2 minus H 2 dash. Okay. So, this particular concept where it is lost? This is lost due to heat equivalent energy expended in overcoming this friction, that is delta Q f. So, when I am performing a nozzle action while moving from 1 to 2 dash in isentropic manner, in reality it does not happen. We will end up in another location 2, for which there is a heat loss in terms of friction, that is delta Q f. So, obviously that is in an this is a negative quantity when this for a nozzle action, but still we can still say that flow can be assumed to be adiabatic without any work and heat transfer. Now, in similar concept also apply here, but here the heat equivalent energy expended in overcoming friction for the situation when of a diffuser action happens to be a positive quantity. So, in the same plot H s, one can say that I am at P 1, I am moving to P 2. So, here an isentropic process would have gone to 1 to 2 dash, but a non isentropic process will take to a real situation and your S 2 also greater than S 2 dash here. And in fact, there is a deviation in the enthalpy, that is H 2 minus H 2 dash. That enthalpy deviation is taken into account of as heat equivalent energy expended to overcome the friction, but in any case the flow is still adiabatic and one dimensional. Okay. So, while analyzing these two, if I can sum up what we have discussed so far for a compressible flow, then these are the summary what we are going to get. That is, when a compressible flow is allowed to flow through a passage in which the area can change, that means we are changing the area, it can compress or expand, that means flow will compress and expand in the direction of the flow with still assumption of steady and isentropic process. Okay. So, this area change has two major effects. So, first effect that we can expand the flowing fluid. So, we call this as a nozzle action, or we can compress the flowing fluid, we call this as a diffuser actions. Now, both the actions are possible and or both the actions help us what to do. That means, if your inflow is subsonic, we can expand the fluid. If your inflow is supersonic, we can still expand the fluid, but what is going to happen, whether we have to either increase or decrease the area. So, it all depends. So, we are bringing the condition of inlet condition into picture, where when your inlet whether the inlet condition is subsonic or supersonic. Now, in that is what in either case or expansion or compression, the flow passage can have increase or decrease in area in the direction of the flow. So, whether you have to increase or decrease, it all depends what condition your inflow is, means whether your inflow is subsonic or your inflow is supersonic. So, accordingly we have to take a decision whether to increase the area or decrease the area to perform the expansion action or compression action. So, now when I say that area has to change, so we have to relax the assumption of constant area situations. That means, there is no question of one dimensionality. So, rather we are going to bring the concept what we call as quasi one dimensional approach. So, in a quasi one dimensional approach, what really happens is that in a normal situation we say the flow to be one dimensional, contained infinite number of streamlines, and we assume this to be a stream tube, and we are really bothered about the inlet and exit conditions, that is 1 and 2, and we say this process needs to be isentropic. So, this was the concept we did for a constant area flow in a stream tube, where the properties vary in one direction. Now, when I say this is a stream tube, we really do not bother about what happens within the area, rather or whether this domain, whether this flow property change happens in any of the manner, whether the process is isentropic, non-isentropic, that does not matter. Rather, we are worried about two extreme conditions, 1 and 2. Okay. So, such a process either within the stream tube, this we can think of heat addition, we can think of heat rejection, we can think of any other phenomena such as formation of normal shock, we can think of any other phenomena such as friction. So, there are variety of mechanisms in which the condition 1 and 2 can change, and all these process are essentially non-isentropic. In fact, this particular part we will be discussing more details in all subsequent analysis. But the very basic point I need to emphasize here, that we really do not about the control surface of the stream tube, because it is a constant area and does not change. And in fact, our all the governing equations which were treated, which was derived, it was essentially following the assumption of constant area. But what we are trying to bring the concept here, a approach we call as quasi one dimensional approach. So, what we are trying to say here, one can have another situation where the flow is isentropic, where the properties do change with respect to increase or decrease in the area of the passage. So, the restriction of constant area is relaxed, means area can change in the direction of the flow. So, how that is possible? So, you bring this particular concept here, is that this is a kind of a situation where we can say the it is a kind of a duct which has certain inlet area A 1 and also some exit area A 2, and in this case the area is changing only in the direction of x. So, I can write A as a function of A x. So, what you see is that there is a flexible surface which is bounded from inlet to exit, right. So, this is nothing but your control surface. So, in this case it is also a stream tube, but it is a flexible. Flexible means I can increase this area, also I can also decrease in area. If I am coming from the other side, like from this side, this is a situation of decreasing the area. If I are moving from inlet to exit, it is a situation is with increasing the area. So, the approach that we do here, like we are in all other cases, we are talking this entire volume to be a control volume approach. It is bounded by the control surface, the properties change in these directions. So, the very basic point that needs to be emphasized, that still we are talking about the although by relaxing these assumptions we say that it is a quasi one dimensional approach in which the uniform flow properties flow properties are uniform across a particular cross section. So, at a particular cross section means I can define the cross section, and these are essentially the cross section at which I can define. So, at this particular cross section, the global it may have a average property value, and that remains same at all the points in the at this location. But if I move to different x, the properties are going to change. So, to some extent it is a logical approximation of actual flow properties. So, at this point also I emphasized that the properties are represented as a function of spiral directions in a flexible stream tube. Okay. This is how we say it is a control volume approach. In fact, while doing analysis, one can say we can think about this overall property change to happen in a very infinitesimally small manner through a small distance dx. If I am measuring x along these directions, so you can define very small elemental lengths of dx, and that dx the property change is very marginal, and while doing so we can make sure that isentropic process assumption still holds good. So, these are already I have explained. Just to go through this, just I can just read out that we are now moving for quasi one dimensional flow analysis, for which we are going to derive the governing equations. So, for in this case we have to consider any arbitrary region in the one dimensional flow through a stream tube. The flow properties in the tube can change as a function of x. So, that means area can change in the direction of the flow, and we can still assume that we can still need to have a flexible rectangular control volume, which is defined by this volume V, and it is bounded by a control surface S. Either you going from one section 1 to 2 or 2 to 1, we can see this area varies, either increases when you are moving from 1 to 2 and decreases when you are moving from 2 to 1. So, the approach that we are following here, that we have to divide this entire volume as a very small elemental length dx, and across which we are going to fit the one dimensional flow equations. So, the first equation that comes out is the continuity equation. So, obviously, the continuity equation is a straightforward, it is a algebraic equations. The very basic difference what we are bringing here, whereas in previous equations we are the area was assumed to be constant, but here we are saying area as A1, that is section 1, and area as A2 here. So, likewise these areas are defined. So, we get a straightforward continuity equations which is algebraic in nature, that is rho 1 u 1 a 1 is equal to rho 2 u 2 a 2. So, otherwise we can say rho u a is equal to constant, then we can differentiate this. So, we will take this form, and moving further and doing simplify, we will use this particular expression d rho by rho plus d u by u plus d a by a is equal to constant. Now, question comes that why we are using this approach, because for this analysis we expect the property change to happen in a very small manner, so that the justification of isentropic process is ensured, and that is possible only when we take a differential approach by dividing the entire control volume through elemental length dx. Now, moving to the momentum equations. Momentum equations essentially it is a not strictly a algebraic equations, because the area changes matters. So, what you see is that from inlet to exit, that is from 1 to 2, what we see is that the area that comes by virtue of pressure is P 1 A 1, that is for this side, and area that comes by virtue of exit is that P 2 A 2, sorry, the press force that get exerted on this exit area is P 2 A 2. In addition to that, there is another pressure term that acts on this control surface, and this changes as a integral. So, pressure changes over that area from A 1 to A 2 over this integrals. So, it is that is what it is not a strictly algebraic equations, but say there is an integral into it. And while recalling the one dimensional equations, the only difference that comes here is this part, where your area is different, and also the integral also was another parameter that gets added in the momentum equations. Okay. Now, this is equation we are trying to analyze the more details. So, moving further, now we have to, so in this is how we get the first equation in the integral form, and what we are trying to look at here, we have to revisit the concept that we are dividing this entire control volume with small elemental length dx or elemental area dA, and area changes from A to A plus dA. So, accordingly, when the area changes this, so the thermodynamic properties, pressure, velocity and density, they also change in a very small manner, like P plus dP, U plus dP and rho plus du. So, difference between between them is hardly a very small number dP. So, this approach we call this as a differential approach. So, for the time being, we this particular equation what was derived earlier from integral calculations, we are going to apply for these two locations having this. So, if I write this equation for this for the figure shown in B, so what we can write is P A plus rho u square A plus P d A. So, pressure is P d A, and in the other side your pressure is P plus d P. So, P 2 will be becomes P plus d P into A plus d A. Also, for this term I can write rho plus d rho. For u term I can write u plus d u whole square. Again for A 2 I can write A plus d A. Okay. So, what you do now? You expand this right hand side term. So, when I expand this right hand side drop, I must drop the terms involving product of differentials. By differential means like rho du square, you will have here du square, will have dA square, will have d rho du, these components wherever it is appearing we have to remove. So, by doing so what we are going to get is that A dP plus A u square d rho plus rho u square dA plus twice rho u du twice rho u A du is equal to 0. Now we have to recall the continuity equation which says rho d rho u A is equal to 0. This we call as from the continuity equation. So, we can differentiate this in a manner, we can write that taking this parameter as 1, we can say rho u dA plus rho A du plus u A d rho is equal to 0. So, you have to differentiate. So, every part these two terms kept constant, keeping the differential of the other. So, this is how we do in the mathematics. Then what we do? Multiply u on both sides. So, when I say multiply u, so I will say rho u square dA plus rho u A du plus u square A d rho is equal to 0. So, when I say rho u square dA, when I say compare this equation, I have here rho u square dA is here, this equation will have u square A d rho, u square A d rho is here. So, these two equations, so the term remaining here, when I substitute here that equation, so I can write this momentum equation it is A dP plus twice rho u A du minus rho u A du is equal to 0. Ultimately, we get A dP is equal to minus rho u A du. So, A gets cancelled. Ultimately, we come back dP is equal to minus rho u du, which is nothing but this particular equation. So, this is a very famous equation known as Euler equation. So, this Euler equation is a very famous equation in the compressible flow analysis. So, essentially we will be using Euler equation for all types of to study the quasi one dimensional flow approach. Now, moving to the energy equations. Now, as you can see the energy equation is still algebraic, because the flow is isentropic. So, total enthalpy remains constant, that is H naught 1 is equal to H naught 2, and when I say total enthalpy is remains constant, that is if I write H plus u square by 2 is equal to constant and differentiate this equation, then we move to the equation, that is dH plus u du is equal to 0. Okay. So, just to summarize the whatever you have studied, I can make out that we are looking a quasi one dimensional flow approach, where the area can change, but this area can change in a particular direction, that is A as a function of x. That is first approach, first assumption of quasi one dimensional flow. Essentially the flow is one dimensional, but it is still not one dimensional, but we are relaxing the dimensionality in some aspect. So, we say it is a quasi. So, while doing so, we derive these governing equations, but our approach would be a, instead of not having a control volume approach, our approach would be a differential approach, while deriving the conservation of momentum equation, that is we will say is a continuity equation d rho u a is equal to constant. We will have Euler equation, that is momentum equation, or in the other words we say it is a Euler's equation, and third one is energy equation. So, this all these things are form the very basic bottom line equations to be studied for quasi one dimensional approach. Now, while doing so, since we have already talked about the situation that the flows, now here the flow can move from 1 to 2, or it can go from also from 2 to 1, and this 1 and 2 are the arbitrary state. Okay. And when I say arbitrary states, these arbitrary states have their own stagnation state. So, that stagnation state we say 0 2 state and 0 1 state. Okay. So, these are stagnation states. Now, when I say these two states, so one can define their own stagnation states. So, to do that we have to use these particular isentropic relations P naught by P. So, that means for the state 1 I can write this as P naught by P 1, I can write this expression as P naught by P 1 by P 1. For this state I can write P naught 2 by P 2. Now, to define all these things we are going to use these isentropic relations where it is a function of Mach number. So, this is a function of m 1, this is a function of m 2, and in fact, this is true for all other properties relations like temperature ratio and density ratio. We also have stagnation speed of sound A naught as square root of gamma T naught. So, this is the very basic form of equations that needs to be used for the analysis which is quasi one dimensional in nature. So, with this I will conclude my talk. So, thank you for your attention.